So, welcome back. This is another lesson on algorithmic design. So, 2 weeks ago at most, we concluded our treatment, our discussion about binary search tree and red-black tree. And today we start a new topic which is related to something you will see everywhere along your career probably. So it's a really important topic, at least from my point of view, and for sure it will be important also from your point of view. So let me go to the slides. Here we are, and let's start it then. Oh, as usual, please let me know if you can see me and hear me. Just send me an acknowledgement on the chat, just to know that I'm not alone. And this is it. So the topic we will deal with today is graphs and algorithms. So I already spoiled you basically the answer to this question, to this small puzzle in which I ask you if you can figure out a way to represent, a unique way to represent all these stuffs. So dynamic systems, for instance, or flows of the information, or spread of infectious disease, as we are seeing during the current lockdown, or dependency relation. So for instance, just figure out a situation in which you want to cook a cake, and to cook a cake you need to in some sense produce a sequential set of operation out of your receipt, and this sequential set of operation are related by some kind of dependency. So before placing the cake on the hover, of course you need to prepare it. Before prepare it, of course you need to buy all the ingredients, and so on, so forward. So this kind of dependency relation can be represented by something, and this something is exactly the same thing you can use to represent dynamical systems or document networks, such as the World Wide Web, or routing systems, or all the things you can see on these slides. On this slide can be represented by using graph. Okay, and just to recall you the meaning of graph, we saw it at the very beginning of this course. I gave you some pieces of information, on what's a graph and how it's built from the graph theoretic point of view. Just let's have a recap of it, just to be sure that no one miss anything. So a graph is a pair consisting into two sets, basically V and E. The set V is the set of the nodes of the graph, and you can represent them just a ball, as you can see on the slide. And the set of set E is the set of edges, which are basically meant to connect. So edges are meant to connect in some sense, to relate the nodes of the graph itself. So depending on the fact that the edges are directed or undirected, you may have two kind of graphs. undirected graph, such as the one you can see here, we don't have any direction to go through on the edges, so you can move from C to E, and from the node C to the node E, and from the node E to the node C, and this is everything you can do on this edge. Or if you may provide a direction, and in that case you can go through the edge only in one direction. So for instance, here I can go from C to E, and in that case I'm dealing with a directed graph, of course. Okay, so it's quite from the graph theoretical point of view, it's really a really simple data structure, a really simple structure. Okay, nothing special. We have nodes and edges. Okay, now what's a path? Well, a path is a sequence of edges which are pairwise connected, so two subsequent edges on the sequence must be connected through a node. So if I go from so this is a path, you can see on the slide the path from D to E, and to go from D to E you have to move along A, B, C and E itself. Okay, this is a path, and the sequence is of course the sequence of this edge, this edge, this edge and this edge. And if you look at two subsequent edges, you end up notice that the destination of one edges, which is in this case B, is the source, so the node from which you are starting, you are leaving, moving along the subsequent edge. Okay, and this is a path. So what's a cycle? A cycle is simply a path moving from an edge and ending up in the very same edge. Moving from a node and ending up in the very same node. Okay, so the final and the initial and the final node coincide basically. And some other small definition about graphs from the graph theoretical point of view. Of course, a graph can be connected or unconnected. A graph connected whether there is a path between every pairs of nodes. So every pairs of nodes are in some sense connected by a path. A connected component of an undirected graph G is a maximum connected subgraph of G. So if you take a node, all the nodes reachable from that node together with all the edges connected that nodes are consist in a connected component, okay, of the undirected graph. There will be a corresponding notion on the directed graphs. We will see it the next lesson probably. And however, as far as the undirected graph concerns, as I said, a connected component is a maximal connected subgraph in G. Okay. So a graph, of course, is cyclic if it contains a cycle, and acyclic if it doesn't contain a cycle. And we talking about undirected acyclic graph. We may define DAGs, which are directed acyclic graphs. Okay, this is it. So how can we represent graph? So what we saw until now is basically a graph theoretical view of what is a graph. Okay, but we need to represent by using a computer. We need to represent them by using computer. So how can we represent it? How can we turn this mathematical notion into a correspondent abstract data type? Well, there are two main ways to represent graph. Of course, there are infinite ways to represent graph, but the two main ways. And the first one is by using adjacency list. Okay, so what's an adjacency list? Well, an adjacency list is a list or an array of lists. For each element of the array, you have a list of the nodes which are reachable from the node corresponding to that element. So every element in the array, in the list, corresponds to a specific node. For instance, this element corresponds to this node. Element number 2 corresponds to node number 2, and so on and so forth. Okay, and the list associated with that element correspond to the list of nodes reachable by crossing just one edge. So from node 1, I can reach node 4 and node 2 by crossing an edge. Okay, so basically this list is the list of edges moving from 1. And of course, the same holds for the second element of the array. So the second element of the array holds the list of edges moving from the node number 2. So as you can see here, from 2 I have one edge moving toward the node number 4, and a self loop. So by self loop, I mean an edge moving from 2 and going into 2 itself. So how can I represent these two edges? Well, simply by noticing that on the second element of the adjacency list, we have two elements, a list containing 2 elements. The 2 elements correspond to the destination of the edges moving from the node number 2. So from the node number 2 I move into the node number 4, and then also from 2 I move into the node 2 itself, and that's how we represent the self loop. Okay, here you can also see a quite interesting case. Here we have a node which does not have which is not an arrival point for any edges, for any edge. So the element corresponding to the third node is empty. It doesn't contain. So the list of the node reachable from 3 without crossing any edge is empty. Okay. And finally, of course, we have the node number 4, which has one single edge moving from it, and the edges reached 2, and this is represented by this list. Okay, so this is quite straightforward representation for graphs, for at least directed graphs, and this way is usually used for sparse graph. So for graphs in which you have not that much, let's say, not that much edges, which is the case. Okay. So how many edges can we have for at most in a 4-node graph? Well, of course, it would be square with respect to the number of nodes we are dealing with. So at most here we may have 16 edges. Okay, because from each node you can reach every from each node you can reach every possible node in the graph itself. So and this holds for all the possible nodes in the graph. So at most we will have 16 edges. but this is not the case. So this representation might be useful for this specific case. Okay, now let's move to the second main way to represent graphs, at least directed graph, which is adjacency matrix. So what's an adjacency matrix? Well, it's a matrix in which each row represent the adjacency, the set of nodes reachable from that row, from that node, by using one single edge. So the first row will represent the first node, the second row will represent the second node, and so on and so forward. Okay, and here, if you take the first row, you see that we have 0 and 1. So 0 means I don't have the edge moving from this node to this node. So there is, for sure, we don't have any node moving from 1 to 1. Okay. While as soon as you see 1, you can conclude that there is a node moving from the node corresponding to the row to the node corresponding to the column. So here we have a 1 in position 1, 2. This means we have an edge moving from 1 going to 2, and this is the case. Okay, so let's see. Here, for instance, we have in row number 1, we are representing the adjacency list for the list of adjacency for node number 1, of course, and here we have 2 non-null elements which correspond to position number 2, to columns number 2 and columns number 4. So here we can conclude that we have an edge moving from 1 to 2 and an edge moving from 1 to 4. Okay, what about row number 2? Well, again, from row number 2 I can reach 2 itself because I have a self loop and 4, and as you can see here, this is the case. What about the third? Well, let me move to the third node. So now node number 3, as you can see, the row is totally, does not contain any one, so is totally null, and that means that I cannot move from 3 to any other node, and this is the case, as you can see. So 3 is totally disconnected from all the other nodes of the graph. And what about the fourth row, which represents the node number 4? Well, from 4 I can reach the node 2, and this is the case. Okay. So again, this is a quite straightforward way to represent the graph. It's quite easy, simple. However, as you can see here, we are wasting a lot of space with respect to the previous representation. Why? Because here we are the space required to represent matrix graphs by using adjacency matrices, of course, is quadratic with respect to the number of nodes, which wasn't the case for adjacency list. So this is an easy way to represent graph, much easier than the adjacency list from some point of view, but as you can see, we are wasting a lot of space in the case of sparse graphs. Okay, and this is all. So now you may wonder, what can we do on these graphs? Well, the most trivial task to be performed on graphs is to visit them. So of course we have we have two main ways to visit. There are infinite ways of visiting a graph. Of course, I can choose randomly all the nodes in the graph. This is a possible way to visit it, but it's not really useful from a certain point of view. We have only two main ways to visit both directed and directed graphs. So the first one is breadth first search, or BFS, which behaves just like a wave. So if you let a drop fall into a glass of water, you can see the wave moving from the source of the wave, so from the drop to the glass. And this is exactly how breadth first search works, so how BFS work, and we will see later on. The second way is by using that first visit, so DFS, and in this case we will see that the visit, so the search will be performed going through so deeper, let's say. So we move along a path until the end of the path, until we can move to a new node, and then we go backward and we try to follow another path, and so on and so forth. Okay, but we will see it later on. First of all, let's move to breadth first search. Oh, by the way, is there any question till now? Can you follow me? I hope so. From time to time, write something on the chat, please, so I know that you are still there. However, so far so good, I think. Let's see BFS, so breadth first search. So the idea is to relate in some sense the visiting order to the distance from the source. Okay, so the lesser is the distance from the source of the visit, the sooner it will be visited. Okay, and because of this behavior, BFS is also used to compute the source node distances. So if you want to know how no questions so far, great. So if you want to know the distance from the source of the visit to a certain node, you may use BFS. Okay, let's see. Well, of course, another important thing that it is produced by using BFS is the so-called breadth first tree, which is the tree of the shortest path from S. So by using BFS, we will be able to compute the shortest path on directed graph or undirected graph from any node of the graph from the source to any node of the graph. Okay, and of course reachable node of the graph. Let's have a look at how it works. Here you can see on the slide a representation for a possible graph. So this is just an example. And at the beginning of computation, all the nodes are labeled by infinity, which is the distance from that node, so from the source to that node. So at the beginning of computation, none of the nodes of the graph are reachable, established as reachable from the source of the visit, from the source of BFS, and we will see that during the computation the situation will change, and at each iteration at each step of our algorithm we will fix this distance. Okay, so the label is let me repeat. The label in the node is the distance from that node, from the source of the BFS visit to that node. Okay. So in BFS we have three kind of nodes. The first one is they are divided in color. Let's say, well, they are not really colored, but they are white, gray, and black. Probably this is because the guy who invented breadth first search was daltonic. I don't know, but I mean, it doesn't matter. The point is that all the nodes in BFS visit are either white, gray, or black. Okay. So white nodes are not been discovered yet. So at the beginning of computation, all the nodes are white. then you select the source of your visit, and the source of your visit will be discovered at the beginning, and it will be colored by gray color. What's the meaning of gray color? Well, the meaning of gray coloring a node is to say that that node has been discovered, so we know its distance from the source, and of course, since the gray color, the gray node on the slides is the source of our visit, of our search, the distance of it from itself is 0, of course. And why gray? Well, gray because despite the fact that it has been discovered, there are neighbors, so nodes which are reachable by crossing just one edge, and that's the meaning of neighbors. There are neighbors of it that are not being discovered yet. Okay, so since this node is white, hasn't been discovered yet, this node stay gray, and this means that this node can be still used to perform a visit, is still useful, let's say. So let's move on, and from this node we try to investigate, to visit all the neighbor of it. Okay, all the available neighbor of it. So from this node I'm moving to this node, and since the distance of this node from the source was 0, the distance from this node should be for sure 1. Why? Because I move to reach this node, I move along one single edge. Okay, and this is it. Now, since I'm moving like a wave, I don't care of the next step. We will not deal with these nodes. Why? Because this node, which was the node, the first gray node on my visit, is still a gray node. So I know that there are other neighbors of it which are white, and then I need to take care of them before moving on these nodes. Okay, so just after discovering this node, which is the first neighbor of the source of my visit, I move on the next neighbor, which is this one. Oh, here we have, and again, since this node is a neighbor of the node I was dealing with, which is the source of my visit, the distance of this node will be 1 again. Now, as you see, I discovered two new nodes. They are all the neighbors of the source of my visit. So this node has no more any white neighbors, and then it became black. Okay. So in the BFS visit, we have 3 kinds of nodes. The first kind of nodes is white nodes, which hasn't been discovered by the visit yet. So here you can see the value labeling these nodes is useless. I mean, because since we haven't visited yet, I don't know the distance from the source to them, and so. For sure, by the end of the execution of BFS, either I discover this node or they are not reachable from the source. Okay, and this is it. So what about the gray node? Well, the gray nodes are the nodes which have been discovered by BFS, but which are still useful because some of their neighbors are still white, so are still undiscovered, while the black nodes are nodes whose neighbors are all have been all discovered, so they are useless from the point of view of BFS. Okay, so let's move on our BFS on this graph. So this was the first node we were dealing with. We move to this, which was its first neighbor, let's say, and this is the second neighbor with respect to the BFS visit. Of course, it doesn't change anything if I moved to this node first and then to this one. Well, of course, it changes the ordering of the node visited, but doesn't change the final result. Now, since this was the first node to visit, first node visited by my BFS, I can move from it to search for new nodes to be discovered, and the only node I can discover from it is for sure this one, which is the white one. So so by discovering it, I can conclude that I can recolor the new node, so the neighbor, the only neighbor, white neighbor of this node, I can recolor it by gray. Of course, I can update its distance from the source, which will be the distance of the node I was moving from +1. And since no more nodes are white in the neighborhood of one can become black. So let's move on. After doing this operation, the next node to be visited is the last node, well, the first node to be gray colored in the list of the node already being gray colored, which is this one. And of course, from this node I can move either to this node or to this node. It doesn't change. I select one of the possible moves, and this is one of them. And again, by reaching this node, I should gray color it, and I should update its distance from the source, as you can see. But in this specific case, this node does not become black. Why? Because I have another node, a white node in the neighborhood of it, which is this one. So let's try to see. Now this node becomes 2, and since no more white nodes are in the neighborhood of 1, this node becomes black. Okay, let's move on quickly. As you can see, it's rather straightforward what's going on until the end. This is the final status, final state of the BFS visit. And here you can see something strange, because this node has not been visited, and its color is still white, but it doesn't matter. This basically means that this node is not reachable from the source. Okay, so once I finish to black color all the gray color nodes, I can conclude that everything has been done. All the possible nodes reachable from the source has been reached, and this node is not reachable anymore. Okay. Now let's try to see the code. This is it. Okay. Let's try to see the code, and let me use the very same names I used on the slides. So first of all, let me define a small function which will be quite useful, and the function will be BFS set. What's the meaning of this function? Well, the meaning of this function is to set some kind of values on the graph. Okay, So we will have as first parameter a vertex. So let me see something. Someone of you asking a question. Under what assumption we choose the source? Well, the source. Some of you is asking how we choose the source. Well, the source is one of the parameters of the BFS visit. So if you call BFS, you may know, you should know, you must know the source of your visit. Okay. The idea is that you want, when you call BFS, you want to know the distance from that node, well, of any node from the source. So you need to provide the source. Okay. It's not a choice. Now let's see. So I was saying BFS set will be useful to update some of the data we have on our nodes. So of course you may want to recolor a node. You may want to update the distance of a node, and you may want to say, look, this node is has been reached by crossing this node, this edge. Okay, and to do it, you don't have to mention the edge. You simply have to mention the source of the edge, and this can be done by using the notion of predecessor. So the predecessor will be the node from which you can reach the node you are dealing with from the source. Okay, so let me draw something just to clarify this point. If I'm dealing with this node V, and this is the source, and the node V is reachable by the source from the source by crossing an edge from W. Well, W will be the predecessor of V. Okay, so so the function BFS set will be used also to specify, to say to the node V, look, your predecessor is this one, and then what, and that's why we are adding here a further parameter, which is the name of the node which is predecessor of V. Okay, now let me delete this one. Okay, now how can we implement this function? Well, this function is really straightforward, because all the parameters but the first one are should be basically a member of the data structure representing the node. So we may say that the color of V is represented by the member color of V. Okay, and what about D? Well, again, the distance of V from the source will be stored in the member D of V. And what about the predecessor? Well, again, the predecessor will be stored in the member predecessor. And def. So this is the function which basically update all the members in all the members of a node. And how to use it? Well, the first thing well, you may say, why defining a function simply to perform this operation? Well, it's easier to understand what's going on, and you avoid to write all this stuff every time you need to use this function. Okay. So the first step in our BFS algorithm, of course, is to initialize our data structure. And if you remember, at the very beginning of our computation, all the nodes were white, and they are all labeled by infinity. So the distance of all the nodes at the beginning of computation, our assumption was that all the distance from the source is infinity. So we may write a function called BFS init, which basically takes the graph itself and a node S, which will be the source of our BFS visit, BFS, and basically set up the things in a way in which all the nodes but the source are of course white. So to do it, we can simply do a for loop for let's say v in, I don't know how to write it, g. Let me write in this way. I mean, depends on how you want to represent g, but you can, I think you can understand what's going on here. So I want, for all the nodes in the graph, I want to set BFS set the node itself. Let me write white, infinity, and the predecessor will be nil. Okay, and this is it. So by executing this operation, I'm basically saying, look, for every node in my graph, at the beginning of computation it should be white, the distance from the source is infinity, and it doesn't have any predecessor with respect to the search tree. Okay, now this must hold for all the nodes but one. Which one? Of course, the source of our search. And so let me use BFS set again for of course S, and it should be gray. Distance from the source, of course, will be 0, and let me say that the predecessor of S should be nil, but just to avoid any confusion with unreachable node, I would say that the predecessor of S is S itself. So at the end of my computation, I will return a tree, which is basically a tree built up by using the predecessor relation, and the only node on the tree whose predecessor is itself would be S, so the root of the tree. And this is more or less all. Now, how can we handle the wave? So if you remember, I said that BFS is more like a wave moving from a drop of water in a glass of water. So the point is that we during the BFS visit we keep keep visiting, taking into account, let's say, all the nodes that are on the same distance from the source. So how can we do it? Well, it's easy to say, well, just look at the gray nodes, but the point is that we need a way to handle, let's say, gray nodes during our computation, and the best way to do it is to use a queue. So to handle the nodes, the gray nodes in our BFS visit, we will use a queue, the queue of gray nodes. Okay, so this queue will store all the gray nodes along all the computation, and as soon as one node will become black, we will extract from the queue, and as soon as a white node will become gray, we will put it in the queue. So the final thing to do in BFS init is to initialize this queue, and let me return also it. So return BFS. Oh, this, let's see, take me away. BFS. No. Oh yeah, BFS. No. I was saying we need to build a queue. So build queue. Of what? Well, at the very beginning, the only gray node will be, of course, the source. So we will build a queue by using S alone. So the only node in the queue at the very beginning of the computation will be S, and that's all. So let me move a little bit upward and right and left. And this is it. And okay, now this is just to initialize our visit. So we need to write the main function for BFS visiting, and the main function to BFS visiting, of course, for BFS, of course, will be called BFS. And of course, you need to take care of the graph you are dealing with and of the source. So these are the two parameters in our BFS visit. We need to deal with the graph, and we need to deal with the source. And the first step to be performed by BFS, of course, is let me write it here, is to initialize the graph BFS init GNS. And by initializing the graph by using BFS init, we will end up with a queue, which is the queue of the gray node. Okay. Now what? While we still have some gray node, we need to perform some operation, and the operation are the one we saw before. So we need to gray color all the nodes well, first of all we need to extract a node from the queue, which is a gray node, and then from that node we need to gray color all its neighbor, and after gray color all its neighbor we need to place them into the queue, and after that for sure, since we gray colored all the neighbor of that node has no more white neighbor, so so it must become black, and so we can remove it from the queue. Okay, so while we have is not empty, so remember Q is the queue, so Q is the queue of gray nodes. So until while Q is not empty, means while there is still a gray node, what can we do? We can extract a node from the queue. So let me call the queue, which basically means extract a node from the queue, and that node for sure will be a gray node. So what can we do? We can go through all the possible nodes reachable from it, and this is easy to be done, for instance, by using the adjacency list representation, because if you have a node, if we have a node, we know all the nodes which are reachable from it by crossing just one single edge, and so let me say for v and here let me write in this way. Okay, so this is just to say that I want to take all the nodes which are in the adjacency of U, which are neighbor of U. Okay, and so for being the adjacency of U, I must check whether V is white. So if V is gray, of course I don't need to do anything more, because as that neighbor has been already reached, and its distance has been already updated, and for sure it is in the queue itself, so that node is already in the queue if it is gray. If it is black, again, its distance from the source has been updated, it is being also removed from the queue, so we don't need to deal with it anymore. The only case for sure which requires some kind of operation from us is the case in which V is white. So if a V color is equal to white, so if this is the case, well, we are dealing with a gray node. We know that from that node we are able to reach another node which is white, so we can gray color the white node and update its distance from the source, and this is done by using BFS set. So this is done by BFS set, which is basically the first function we wrote today, and so we want to change the properties of V, and we want to gray color it, and we want to update its distance from the source. Well, the distance from the source of V for sure will be the distance from the source of U, and you remember, once I have gray colored one node, I've already evaluated its distance from the source. So the distance of the color of V will be the distance of the color from of D plus 1, of U, sorry, from plus 1. So I reach V for the very first time by going through U, by crossing an edge from U. So the distance from the source of V for sure will be the distance from U plus 1. And what about the predecessor? Well, the predecessor, of course, is U. And this is it. Now, once we have gray color V, we must include it in the gray color Q. And so let me use NQ, which will be a function simply to put inside the queue a new node, and this is it, and this is all about the node V. So once I perform all this operation on node V, for sure V is has been updated, has been included in the queue, and nothing more should be done until the extraction of V from the queue. Okay, so and 4, and what's next? Well, what's next? Once I've performed all this operation on all the neighbors of U, I'm guaranteed that all the neighbors of U are different from white, are no more white, so no more white neighbor of U. And then, since for sure we don't have any neighbor of white neighbor of U, U can be black colored and removed from the queue. But U has been already removed from the queue at the very beginning of our while block, and then the last thing I must do is to recolor U. And to recolor it, we can simply do U color black. And this is it, I guess. Let's see. Yes. And this is it. Okay. Now, during my presentation I said that BFS will return will visit all the graph, will return for every node reachable, for every node in the graph, the distance of that node from the source, but also return a tree. As I said, the tree is specified by using the predecessor function. Okay, so you may want to rebuild the tree if it is necessary, but is it is also, well, actually the tree is memorized, is stored into the graph. So if you want to know how to reach a node, a generic node W, you simply have to look at the predecessor of W, at the predecessor of the predecessor of W, and so on and so forward, until you end up in the source, and you can deduce the source by searching for the only node in the graph whose predecessor is itself. Okay. Now let's try to evaluate the complexity of this stuff, of this search. So BFS set, which is the first function you may see on the left. So this function, of course, takes time. Theta of 1 is constant. Okay. What about BFS init? Well, the BFS init spends of course theta 1 for every repetition of the for loop. The number of repetition of the for loop depends on the number of nodes in our graph, of course. This BFS set theta 1, again, this build queue, well, of course, may depend on the number of nodes I want to include in the queue itself, but since here we are inserting just one node in the queue, takes constant time, will take constant time. So the overall cost of our BFS init function will be theta of cardinality of V. Well, V is the set of nodes in our graph. Okay. Can you send me an acknowledgement just to know that you are still there, please? Pretty please. Is it everything clear up to now? Please ask some question, say something, write something. Okay, let me move, in the meanwhile, let me move to, yep, great. So, let me move to BFS. So, the total cost of BFS will be, of course, will depend, of course, on BFS init. We said that BFS init takes time, which is theta of cardinality of V. And this is for this stuff. We have said that BFS set takes time theta of 1, so constant time. Now, enqueuing something into a queue is not, of course, difficult and takes time constant, takes constant time. So again, this is theta 1. So the overall if block takes time theta 1, and here we have to evaluate this stuff. To establish the total cost of this for loop, we have to evaluate this stuff. Of course, you may say that the overall number of possible neighbor of V is the cardinality of V, but this is an overestimation actually, and you see in a while you see why in a while. Okay, so once basically just observe one single thing. So once you extract something from the queue, is no more inserted in the queue, because to be inserted in the queue, either you are the source or you must be Y. And since the insertion occurs exclusively for gray nodes, once you are the queue, once a node has been the queue, never be included again. Okay? So basically this for loop say that for every node extracted from the queue, I want its neighbor. So I'm basically taking all the edges moving from U to other nodes. But since this is done for all the U in the node, the number of times I'm repeating the block of the for loop is proportional to the number of edges in my graph, which may be far less than the number of nodes at the power of 2. Okay, so let me repeat. This block, so the block containing the if statement, the if a conditional statement, is repeated a number of times which is proportional to the number of edges in my graph. And this is quite easy to see, because this for loop, so the for loop, take all the neighbor of one single node, and that node can be included into the queue exclusively once. So if I dequeue it, it couldn't be included again. So if this for loop for every U take all the edges moving from it to another node, I'm basically performing a for loop along all the possible edges of the graph. And that's why the overall cost of all this stuff, of the for loop, the overall cost along all the repetition of the while loop, of course, along all the repetition of while loop, the total cost of the for loop is theta of cardinality of E. Of course, the dequeue operation and the black coloring operation takes time theta of 1. Oh, this is not, sorry, this is not theta, of course. This should be big O. Why? Because if the graph is not connected, there are part of the graph which weren't included into our, which will not be included into the computation, and so some of the edges may be not, how can I say, traversed. Okay. And that's all. So how many times I perform this dequeue at most? The number of times I perform this dequeue at most is, of course, equivalent to big O of cardinality of V. Again, why? Because it may be the case that some nodes are not reachable from the source, so at most I reach all the nodes. I must dequeue all the nodes in the graph, because they may become they should become black. So they are become gray and they should become black, and so I must dequeue them. But this is an upper bound to the number of dequeue I must perform. And what about this one? What about the black coloring? Well, again, so it really depends on how many gray nodes becomes gray, and this depends on how many nodes are reachable from the source. So at most they will be cardinality of V. So the overall cost of this operation will be, let me repeat it. So will be time of BFS on Z. Well, let me explicitly mention DE will be equal to the cost of the initialization, which is as we saw theta of cardinality of V, plus the cost of the for loop iteration, which is big O of cardinality of E, plus the cost of the queuing all the nodes and black coloring them, which is big O of cardinality of V, which of course belongs to big O of cardinality of E plus cardinality of V. Okay, that's all. So to BFS visit a node, we simply have to perform all this operation, and the cost of this operation is big O of the cardinality of V plus the cardinality of V. Easy. So again, how can we extract the path from a possible node from any node to the source? Well, it's quite easy. We can write, let me write the piece of code. So the function to extract it, definition, extract path. And so from, let me say V, for instance, I want to know the path from the source to V, the shortest path from the source to V. How can we do it? Well, once we have executed BFS, we have updated all the property of V, and in particular we have updated the predecessor property, so we can exploit it to get the path. Okay, so let's say we have a list, the path is a list, so well, we can also use an array, so path say array of what, of which size? Well, the size will be, of course, the distance of V from the source plus 1. Why plus 1? Well, because the distance of the source from itself is 0, and since we want to include also the source inside our path, we need to include it. And so let me write, let me use another variable, let me call it I, and will be set to d plus 1, and this variable will be the variable So this variable will be the position in the path we are dealing with. So at the very beginning we want to insert inside our path the node whose distance is I minus 1. Okay, and so while let me use another variable. Well, no, it's okay. While the predecessor is different from V, what can I do? Well, I can include into path in position I minus 1. Well, no I minus 1, but I, sorry, in position I can include V, and then I can decrease I by 1, and this is it, and while when this condition occurs, I'm dealing the I need also to update, I missed to update V, of course, so let me change here. V will be equal to V predecessor, and while when this condition doesn't hold anymore, I'm dealing with the source of my tree, so I simply need to add to path 0, not 0 but 1, of course, or I will be equivalent. What B, and this is it, and then we can return path. Of course, at the very beginning of the computation, so here, let me say here, we may want to handle non-reachable nodes. Okay, so it may be the case that some nodes are not reachable at all, and they are quite easy to be pinpointed, because you are simply you need simply to have a look to the predecessor. So if the predecessor of a node is nil, for sure they are not reachable, and this is it. Let me try to answer to one of your questions. But the cycle is inside the while cycle. Why don't we sum and multiply the asymptotic behavior? Okay, so someone is asking, let me go back to the code of BFS. This is the code of BFS, and can you see it? Yeah. So someone is asking, why can we simply evaluate the number of operations performed by this for loop, and then multiply by the number of time we are repeating this while loop? Well, we did it basically. Well, we cannot did. Well, it was wrong. We cannot do it simply because the number of neighbors of a single node depends on the node itself. So they are not always the same. So a node may have one single neighbor, and another node may have, I don't know, 2000 neighbors. So you may provide an upper bound for the number of neighbors of all the nodes in the graph, and the upper bound would be of course the number of nodes in the graph. So if you upper bound this for loop by saying, okay, the maximum number of nodes which are reachable from you by crossing one single edge is at most big O of cardinality of V. If you do it, the total complexity of your algorithm would be big O of cardinality of V square. Which is not wrong, but actually it's much more than a big O of E. Why? Because if your graph is sparse, so if the number of edges in your graph is much less than the square of the number of nodes in your graph, then the complexity you are providing is much larger than the reality. Okay, so the best thing to do in this case is to try to understand the overall number of time you are repeating this if condition, and to do it the best way to do it is just by observing that here this for loop globally is performed a number of times which is equivalent to the cardinality of the number of edges. So every time you perform this for loop, you are dealing with a different edge in your graph. Okay. Again, if you try to compute the complexity as you suggesting, one of your colleague was suggesting, so by computing upper bounding the complexity of this for loop and then multiplying that complexity by the number of times we are performing the while loop, this is not wrong, but you are providing an upper bound which is much larger than the one we got by observing that this for loop is performed globally a number of times equivalent to the number of edges in the graph. Okay, just to let me delete here to avoid any confusion, but let me just observe one last thing. So we saw that by computing the complexity as you suggested, so by evaluating an upper bound for the for loop and then multiplying it by the upper bound of the while loop iteration, we end up with a complexity which is big O of cardinality of D at the power of 2, and that is that set of course includes all the functions which are in big O of cardinality of E. So it's not wrong, but I mean, okay, if the graph is not sparse, this is not even an equality. So you are in some sense overestimating the cost of your operation. I hope this is clear. I mean, it's a really subtle way of computing the complexity. Again, so let me answer the last question. I'm not saying that when I say that this for loop is performed globally cardinality of E, I'm not saying that this for loop is performed cardinality of E times the number of iteration of this while loop. I'm saying that in all the iteration of the while loop, the number of iteration, the sum of all the iteration of the for loop is big O of cardinality of E. Okay, and again, this is quite easy to see, because at each iteration of the while loop I'm dealing with a different node, and at each iteration of the for loop I'm dealing with all the edges moving from that node. So at the end I cover all the possible, at most, all the possible edges in the graph. So if I had a counter if I had a counter counting how many times I'm performing this if block, if condition, if statement, as you prefer, the number of time I'm repeating this statement is at most, along all the computation, is at most cardinality of E. So I don't need to multiply it by the number of time I'm repeating a while loop, because it's an overall computation. Okay, just to clarify the point, I'm not going to, so this is not a functional change to improve BFS. It's just meant to let you understand what's going on. Okay, so let me add another variable. Let me call it counter. Yeah, counter. And let me add here counter. So by using this arrow, I mean I want to place this instruction there. Okay. At the end of computation, counter can be at most equal to the number of edges in the graph. Okay, great. So let me change again the code. This is just to clarify the point. Okay. I mean, it's a different way of computing, so different from what we saw until now, of course, a different way of computing the complexity, but as you see, by using this way, which is a global analysis instead of block analysis, this global way of computing, of evaluating the cost of a function, give us the chance of being more accurate, let's say. So our complexity is much more accurate with respect to the one we may get by counting the blocks and multiplying by the number of iterations. So this is all for today. Tomorrow we will see DFS. Not tomorrow. This is Tuesday. So on Thursday we will see DFS. Again, for any request, clarification, question, so on and so forth, send me an email. We may think to have some kind of question time for in the future for specific question. ad personam, so for a single of you or for all of you, as you prefer. Just let me know what's going on, if you can follow me, and if you enjoy the course. Okay, so thank you so much, and see you on Thursday then. That's, I think, all for today, and see you then. Bye.